Good evening, everyone. My name is Scott Kratz. I'm the Vice President for Education here at the National Building Museum. And tonight we present a program in our long-running series, For the Greener Good, Conversations That Will Change the World. Tonight's program is entitled Life After Plastic. We did a great the discussion over dinner with the panelists, and I think we're in for a fantastic discussion. Our 2011 series of For the Greener Good explores building materials and sciences. New and old technologies play a critical role in creating more sustainable structures. A quick program note before we begin. On March 24th, we continue the series with the next program, provocatively entitled Historic Preservation versus Sustainability? ? We have saving existing buildings as an inherently green strategy, but how does a community balance the historic fabric of vernacular architecture with the need to bring older buildings up to modern environmental standards? Panelists will include the newly appointed Chief Greening Officer for GSA, an architect and product designer, the Vice President for LEED at U.S. Green Building Council, and it will be moderated by our Senior Curator here at the Museum, Martin Moeller. And for the second time this year, we are live tweeting tonight under the hashtag #FGG. We encourage you to chime in on your conversation and ask a question. The For the Greener Good series is presented by the museum's sustainability partner, the Home Depot Foundation, and we'd like to thank them for the generous support of this innovative lecture series. And programs such as tonight have been organized to make sure that we're engaging in a larger conversation, not only for people up here on the panel, but also with you all. So we're going to be breaking periodically to take Q&A about midway through the program, and then again at the end. So start thinking about what some of the questions are that you want to ask. And before we begin, it's really helpful for the audience, or for the panelists, to understand sort of who's in the audience, who they're speaking to. Can I get a show of hands if there are architects in the audience? Great. Planners? Great. Landscape architects? Wonderful. Engineers? It's okay for the panelists to raise your hand too. Students? Great. Fantastic. And federal or state employees? Wonderful. That's great. That is extraordinarily helpful. Thank you. So let me give a quick introduction to our moderator, who is then going to give a very brief presentation to put tonight's discussion in context. And then, in turn, Lance is going to introduce our distinguished panel. Lance Hosey is President and CEO of Green Blue, a nonprofit research institute dedicated to making products more sustainable. An architect and designer, he is former director with William McDonough and Partners, and is a contributing editor, with Architect Magazine, where he wrote the monthly ecology column from 2007 through 2010. With Kira Gould, he is co-author of Women in Green, Voices of Sustainable Design in 2007, the first book in the design industry to study the connections between diversity, innovation, and the environment. His forthcoming book, The Shape of Green, Aesthetics, Ecology, and Design, or How Beauty Could Save the Planet, demonstrates how form and image can enhance conservation and community at every scale of design, from products to cities. With that, please welcome Lance Hosey.
Since we are live tweeting, I'm going to try to keep all my sentences to under 140 characters, and I hope you'll do the same with your questions. So I'm going to give a few introductory comments and then bring up the panelists and introduce them, and then, as Scott mentioned, we'll have a discussion amongst us and then open it up to all of you and do that back and forth for a little bit. As Scott mentioned, I co-wrote a book a few years ago called Women in Green, Voices of Sustainable Design, and since Kira Gould and I wrote that book, this might be the first time I've been on the stage with all men, so it's a sort of a new experience for me. And I will introduce, but they're fine gentlemen, and I will introduce them all in a couple of minutes. So the theme of tonight's talk is life after plastic, and I think before we can try to imagine what life after plastic will be like, we have to imagine what life before plastic was like. So it was just invented in the 1850s, but it really didn't take on until the middle of the next century. And now it's in virtually everything we make, from toys, phones, and computers to cars, airplanes, and buildings. The rubber ducky, which you've already seen, is actually not rubber. It's typically PVC. And 40 years ago, plastic was considered the miracle material. I'm sure you all remember this iconic scene from The Graduate. So, and the reason why it seemed to be the miracle material is because it's versatile, pliable, durable, light, cheap, easily cleaned, and that's why it's in virtually everything we make. Now, 40 years down the road, the future in plastics was not quite as bright as we imagined 40 years ago. The source and supply, if you read the intro to tonight's event, it focused on the fact that plastics are petroleum-based, and I don't need to tell you what the issues around petroleum are, though we make something like 300 billion pounds of plastic every year, so clearly it's a big part of the petroleum challenge. In production, there are also challenges. It's made in highly toxic and dangerous petrochemical plants, generally speaking. During much of plastic production, dioxins are released that during the process gets into the lungs, skin, and other organs of factory workers who have high rates of debilitating illnesses. Factories also tend to be in poorer communities where they create serious environmental health hazards, polluting the air, water, and soils. And then in use, someone once told me that if you want to engage an audience, that at some point in your talk you need to show either a baby or a puppy, or both, preferably. So I've got babies and rubber duckies here. Of course, the comments I'm about to make are sort of dark, so I don't know whether the lightness of the baby will die in a second. So PVC, which is one of the more familiar plastics, is the second largest plastic commodity. Still popular in the U.S., though it's been banned in 14 other countries and the EU. For a number of reasons, probably because it creates serious problems. It's been linked to serious problems in children, including asthma, obesity, autism, hormone disruption, and learning disabilities. And the toxins in PVs, many studies show, are so prevalent that virtually everyone tested ever has traces of them in their bodies. It builds up in the fat tissue in your body, essentially. And then in disposal, there are equal challenges. Less than 5% of plastic gets recycled. So much of it ends up in landfill where it never breaks down. It's virtually not degradable at all, most plastics, that is. Except for the small amount that's been incinerated, which is a very bad idea, every piece of plastic ever made still exists. Much of it ends up in the third world, where we dump it on the world's poor. This is a particular village in China which has been dubbed the e-waste capital of the world. And much of it ends up in the ocean. This map here, there are two gyres in the Pacific where an estimated, I see varying estimates of the size of all the plastic and trash and marine debris in these gyres range from the size of Texas to 1.5 times the size of the U.S., which is why it's been dubbed the eighth continent. So, and this is the National Building Museum. There's a lot of plastic in buildings. It's in virtually every aspect of buildings: roofing, siding, plumbing, cabling, cabinets, flooring, furniture. So clearly, as we think about what it means to green the building industry, then plastic becomes a serious challenge. So, let's bring up our panelists and talk about how we might address those challenges. So let me introduce these guys, and as I do, maybe you could come up as I say your name so we can do this very formally. Jay Bolus, who is right here, is Director of Science and Vice President of Technical Operations for the Sustainability and Product Consulting firm McDonough Brown-Gart Design Chemistry, or MBDC. I like guys who have two titles. That seems a little greedy to me. Jay essentially steers the Cradle-to-Cradle product certification program, which many of you are familiar with. It's sort of the centerpiece of MBDC's operation. Blaine Brownell is an architect whose research focuses on emergent materials. He is the principal in design research practice, Trans Studio, and director of the Master of Science program, Sustainable Design, at the University of Minnesota School of Architecture. Many of you may know Blaine's series of books, Transmaterial, which is the architect's go-to guide to emerging materials and products. His forthcoming book from Princeton AP is called Matter in the Floating World. And then finally, Bob Peoples here is director of the Green Chemistry Institute, the American Chemical Society. Formerly, he was the sustainability director for the Carpet and Rug Institute, executive director of the Carpet America Recovery Effort, otherwise known as CARE, and president of the Environmental Impact Group. So Bob knows a lot about carpet, and there's a lot of plastic in carpet, so we'll probably talk quite a bit about that tonight. So I'm going to sit down. Any questions at this stage about these guys? We unfortunately don't have placards. We do have placards, but we're choosing to sit on them, so you won't be able to. Yeah. So that's Bob. This is Jay, Blaine, and I'm Lance. So I'm going to start with Jay, and I painted a pretty dark portrait of plastic just then, but is all plastic necessarily bad?
That is a. Well,
I'm starting with a really narrow.
Yeah, that's a great question, because that is sort of the theme of what we're here to talk about tonight. For those of you that don't know what Cradle to Cradle is or what that philosophy is all about, actually, can we get a show of hands? How many know what Cradle to Cradle is? Read the book or know that? Okay. So we envision products as existing in one of two metabolisms. There's the technical space, where those are the materials that you should be recycling over and over again because they have some intrinsic value and they can't go back to nature safely. There's the biological metabolism for those products that are made of things that can go back to nature safely and should. So they should be composted and the nutrients returned to nature. Those technical materials and those technical metabolisms should be recycled over and over again. So there's an opportunity to take plastic that's designed intelligently and doesn't have a lot of the toxic characteristics that Lance described earlier. So if you make a plastic material correctly and keep it in this technical metabolism of constant recovery and reuse, plastic can be a very good thing. You know, we think that oils are really valuable raw material, too valuable to be burned. It should be used for intelligent materials like plastics, but plastics that are safe for humans and the environment throughout their use, and that can be recaptured, reprocessed, remanufactured, recycled perpetually.
So it sounds as if you're saying the theme should be life with plastic. I asked these guys earlier, I said, I think we probably all have a similar point of view, and it would be nice to mix it up a little, and it turns out that we don't necessarily have the same point of view. And I think you and Bob both said that you felt that plastic is here to stay. Is that correct?
I believe it is. I obviously won't speak for Bob. I think he can do that by himself.
Yeah, but I would agree that I think plastic's going to be with us for a long time. Transitions take a long time, and I'm a believer in sort of the model that nature has perfected over the millennia called evolution. And we have to evolve, increasing our understanding over time. We keep what works well, and we get rid of what doesn't work well. And we now, with the modern tools of mechanistic toxicology and molecular biology and all the omics that you hear about today, we're beginning to understand how these synthetic materials we've made over the last century or so interact with living systems. And we know some of them are problematic. But again, it takes time to solve all these, to understand the complex systems and come up with replacements going forward. I guess the one other thing I'd say about plastics is that I think you have to dig very deep to understand all of the issues when you talk about materials, because we use the word plastic, but there are many different kinds of plastics derived from many different kinds of feedstocks. And if you take one step further back than that, less than 10% of all the oil that's consumed on this planet every single day, and the number is about 85 million barrels of oil a day are consumed on this planet, less than 10% of that oil winds up going into chemical manufacturing operations for plastics or other fundamental building blocks or feedstocks. So having said that, the big challenge for us is, can we come up with materials that are benign by design? And I represent green chemistry, so maybe we'll have a chance to talk about that a little bit later. But develop materials that are benign by design and materials that are derived from something other than petroleum. bio-based feedstocks, rapidly renewable feedstocks, but not feedstocks required for food. And that's another issue that we can get into later.
Sure. Oh, while you're on it, why don't you define green chemistry? So again, Bob is the director of the Green Chemistry Institute, so we should know something about green chemistry.
Green chemistry is defined as the goal is to reduce or eliminate the use and or generation of hazardous substances. Doesn't matter whether it's the drug that you're trying to make as the primary product or the waste stream that comes from that drug or materials that are used during the manufacturing process to make a product out the back end. Our goal is to reduce or eliminate the hazardous materials associated with the product or the materials that are used to make the product. And I would probably like to add that green chemistry as a concept has been around for about 20 years now. So I like to tell people it's not an academic curiosity. It's a proven systems approach using fundamental design principles to avoid the creation of problems in the future. So we have hundreds and hundreds of regulations in the United States and thousands around the world that deal with chemicals, right? The reason we have regulations is because people realize problems were created as a result of these materials getting into the environment. So the way you deal with the problems is to create a regulation to avoid the ongoing problem. If you can apply the principles of green chemistry successfully, the goal is you won't need to have regulations because these will be benign materials.
So using that definition of green chemistry, and I'll just put this question to all of you, would you say there is a green plastic in existence today that meets all those criteria you just listed?
Yeah, I would say there are. I mean, from our perspective, our favorite plastics are a group called polyolefins, which include your polypropylenes and polyethylenes. Generally, the process to manufacture them, while not completely safe, is much better than the vast majority of the plastics. Once the plastic is made, it has lots of uses. Typically, it can contain toxic additives, but in most cases it doesn't. Both of those plastics are recyclable and are currently being recycled. So the whole spectrum from the horrific plastics like PVC you mentioned, PTFE, some of the halogenated plastics, to the green end of that spectrum, I would say that the polypro and polyethylene are down at that end. Now on.
Well, the only thing I'd add to that is that we tend to look at things as a spectrum. So our goal is to always get greener. We're evolving with our knowledge as a function of time. So the goal is to get greener. And there are plastics that are greener than others. I'm not sure that if you look at both the holistic viewpoint of how do you make the material and what is the material itself and the building blocks from which you make it, there's probably nothing out there that we would call truly green. Maybe cellulose that you get from trees, things that come from nature, because you've got that closed loop recycling capability. But man-made materials, most derived from oil today, are not. They're going to fall across some spectrum of green. I don't want to overdo the chemistry side of this thing, but I do kind of want to make a point because we talk about PVC, and I'm a person that tends to believe that PVC is a misunderstood plastic. So PVC, the polymer itself, inherently is not necessarily a bad thing, and there are people that can flywheel PVC through the system. The problems with PVC come from its manufacture because you start with a basic building block. So if you look at a building made of brick, you see a holistic building, but you know that each individual building block of that building are the individual bricks. Well, the individual building blocks of the polymer that we call PVC is vinyl chloride monomer. Really bad actor from a human health and environmental point of view. So that's a contributing factor to the negatives associated with PVC. The second thing is PVC is a hard plastic. But your shower curtains, the rubber ducky, they're pretty flexible, right? The way we get them flexible is we put some additional chemicals in that plastic called plasticizers. And plasticizers, certain classes of plasticizers are known to cause some human health and environmental problems. So if we could find a way to have plasticizers that are do not have any harmful effects for human health or the environment, or we could find a way to develop a polymer that's just like PVC, but you don't have to go through vinyl chloride monomer, that's not a bad step in the evolution of trying to create useful, functional, proven materials that reduce impacts on human health and the environment.
I'd like to take a stab at your question, Lance, and also reflect a little bit to the previous discussion about the topic tonight. And it's interesting when you look at plastic and the history of plastics, plastikos, the Greek word that was borrowed to describe this family of materials, happened not as a kind of direct, quick process. It was actually almost a kind of compromise word to try to describe these new kind of foreign materials like bakelite or celluloid and other materials that largely came about trying to replace more valuable virgin materials like ivory, let's say, with a cheaper durable substitute. So it's interesting because if you look at that side of it, these modern synthetic plastics that largely are derived from petroleum came from that kind of origin. Now, there are certainly economic factors there. Seem like a good business plan, for example. But so we're dealing with and as these guys have said, we're dealing with a family of materials that are so different. And I think most of us know that and other chemists have said that, well, PVC compared with another plastic, they can be as different as glass and concrete, or speaking very generally, but they're very different. And so I think inherent in the topic, or the title, Life After Plastic, is that first sentence, this connection with oil, obviously, because a lot of the plastics we're familiar with come from oil. But at the same time, there are, as many of you know, a lot of plastics that don't come from oil. A lot of new bioplastics research. Now, there's still, in most of those bioplastics, there's still some ingredient, not all, but some component that's still derived from oil. But increasingly, we're seeing plastic made from different types of materials, renewable materials. And so I think it's in that title, Life After Plastic, there's a kind of inherent contradiction. There's an assumption that, well, it's after cheap oil, let's say. And so I would simply reinforce this notion of a gradient, as well as just, I'd like to, as the architect, and Lance, you're an architect too by training, it's important too to realize that a lot of what we're talking about so far is cradle to gate, so-called cradle to gate. Not all, but the material chemistry. We're talking about what's inherently in the product before it leaves the factory, let's say. And so much of a product's life, as Lance, as you showed with the gyres, and as well as the kind of use of the product, is somewhat known, but a lot of it's not known. And so I think that's another important factor to understand. And I think scientists are becoming, and architects certainly are becoming more aware, have a lot of catching up to do to understand what happens after that first life. We're so focused on that shiny package or the new building. What happens to this material after that first life?
Well, Blaine used a word that kind of caught my attention here in particular, and that is economics. And for the successful implementation of green chemistry going forward, we say there's three things required. The first is you have to have functional performance as good or as better than what you're trying to replace. The second thing is we would like to get the green chemistry right. But the third part of the triangle is you better get your economics right. And I think therein lies one of the fallacies that we've got to overcome here, and that is that ultimately society has to bear the cost of sustainability. We've kind of had a free ride, because if you think about it, when you're done with something, what do you do with it? You throw it away. Can anyone in the audience tell me where away is?
Gyre.
Yeah, well, it's the gyre. Well, realistically, if you go back to the fundamental principles of chemistry and physics, we know that there is no such thing as away, because we don't destroy matter. We can interconvert energy and matter, but it doesn't get destroyed. My best simple example for you is if you take a glass of water, and you take a drop of blue ink and you put it in the glass and you look at it, what do you see? You see a little dot of blue ink, right? But if you come back an hour later, do you see the blue ink? It disperses. It disappears. You can't see it, so it's out of sight, out of mind. But the fact is, we know from a scientific point of view, all the molecules that make up the blue ink are still there. So we've been throwing things away, not worrying about where away is, and away is starting to come back and haunt us right now. And it's things like the Pacific Gyra, it's the body burden that every one of us carries. It depends on who you talk to, but we've got between 200 and 250 synthetic man-made chemicals in our fat, our blood, and our urine when you do the analysis of it. And it's ubiquitous across the entire planet. So we have to get our minds around the true cost of sustainability if we're going to solve these types of problems going forward.
Jay, Blaine mentioned bio-based plastics. You want to talk about that?
I think that's a really fascinating area and something we should talk about, because that sort of breaks the oil-plastic continuum, if you will. And it's relatively new compared to how long traditional plastics have been around, and I think there's huge opportunity there. Now, it's not a perfect solution either. You know, Bob mentioned earlier we have to stop looking at food-based biomaterials as a source for our plastics and start to look at other bio-based materials that maybe are agricultural secondaries or come from other places other than the kernel of the corn or the soybean or what have you. So that's, you know, there's some work that needs to be done there, and there's still a lot of petro-based things in those plastics. So to go truly bio-based is going to take some time, but I think that offers some really interesting opportunities.
Mm-hmm. Have you guys seen the study that came out of the University of Pittsburgh last fall? Bob, you mentioned a spectrum of what's green in this case, and they ranked 12 different polymers across the spectrum, with PVC being at the worst end. And what was interesting is that the other end, conventionally harvested bio-based plastics actually performed worse than some conventional petroleum-based plastics, but then at the extreme end of the good spectrum was sustainably harvested bio-based. So I think it's important when we say bio-based to distinguish between plant materials that are conventionally harvested because of all of the gigantic environmental footprint of conventional agriculture, and being smarter about how we harvest those plants. So that's the kind of spectrum you were talking about, right, Bob?
That is right. And if I could build on your observation, I would say that it's not just transitioning from petroleum-based to bio-based with all the considerations we just talked about, because there are some good bio-based polymers out there today, one called polylactic acid, and you can find it in compostable picnic plates and utensils. You can find it in food packaging and bottles and some of that stuff. The problem is that's a compostable material, and we don't really have good industrial-scale compostable facilities, nor do people recognize that these materials are compostable and should be put in a stream that can be recovered and put into a compost system. So we are still, again, evolving our understanding and our infrastructure to meet those needs going forward. So to me, one of the biggest challenges we face is awareness. The first thing we do is we have to make people aware that some alternatives exist. Then once people are aware, then you can start providing education and information to how do you plug into, how do you take advantage of these alternative systems. And then we have the economy of scale that kicks in, because when you buy the first iPad, you pay a premium for it. And then when you make millions of iPads and you got competition, the price comes down based on volume and experience. So the same thing will be true as we begin to bring these alternate, better, greener materials into the marketplace. We'll get the advantage of economy of scale, and we'll start to penetrate based on awareness, and we'll make progress. And we are making progress. It just happens to be slower than I think some of us would like to see it at this time.
I'd just like to add something to that. I had a conversation recently with David Stanton with NatureWorks, a Cargill company based where I live in the Twin Cities, and they make the resin that kind of is most competitive, I think, in the market, the PLA resin. And I asked him about this question about corn, because there have been some concerns. Well, corn uses petroleum-based fertilizers, and industrial agriculture there's some controversy around the greenness of that, and as well as all the fuel and everything. And he said, look, we chose North America to develop NGOs, the name of their polylactic acid-based bioplastic, because of the healthy economy here. and corn, because that was the most viable agricultural source from which to make our plastic. But they already have their sights set on other types of agricultural products as well as other nations in which to do business. This is just kind of early innings, and I'm not necessarily qualifying whether corn was good or not as an initial start. But his point is that it's incremental. Sure. They're really building their business, and he said that the future that they like to see sooner rather than later is cellulosic-based bioplastic, which is from inedible substance, and so it doesn't compete with foodstuffs, and presumably it has a more robust potential for better plastic.
So there's petroleum-based plastic, there's corn-based, which has its challenges because you're competing with foodstuffs, and then there's cellulose-based. What else is there? What's coming down the pipe?
Soy-based, sugar-based. It's possible to make some plastics that are currently coming from petroleum feedstocks from biofeedstocks. So polyethylene, which is one of the plastics that I mentioned earlier as being sort of one of our greener plastics, can actually be made from sugarcane as a starting block instead of ethylene coming from cracking of gas or petroleum feedstock. So there's lots of different bio starting blocks that they're looking at.
Any of those that any of the three of you are particularly fond of versus the others?
I think because Bob touched on this, and to me the building block is not as important as what happens at end of life. Mm-hmm. Because no matter what we do, if we continue to throw stuff in landfills or into the Pacific Gyre or into incinerators, we're never going to have a sustainable solution. We're always going to have to grow more sugarcane, more corn, more soybeans, whatever it is. So even if we stay with petroleum-based plastics, but are able to keep them in closed loops of reuse and remanufacture, we'll be much better off than we are today. So I don't really feel like the problem is so much where the feedstock lies as what happens at end of use phase. I want to say end of life, because I don't feel there should be an end of life, but it's end of the original use phase.
Well, it's a great question because I wanted to ask you offline, but I'll ask you in front of everybody now. Because you mentioned that the centerpiece of the cradle-to-cradle protocol was technical versus biological cycles, and I've been hearing a lot from people that we work with that they feel that waste to energy is a smarter strategy than composting, meaning that if something can go back to the earth, then it'll biodegrade and become part of the soil, that process is actually not as smart as using that waste material to feed back into the industrial cycle. And whether or not you agree with that, first I'd like to know how you feel about that. But it made me wonder whether I think one of the cornerstones of cradle to cradle is those cycles never cross. But wouldn't waste to energy be an example of those two cycles crossing?
Well, in essence, we like to talk about them as separate cycles that don't cross, but they're actually nested. If you think about it, the technical sits inside of the biological. Because laws of entropy tells us things are going to get out. Your blue dye example, things disperse. We can't do anything about that. So they are nested. But the waste to energy is a really interesting alternative. Ideally, you'd like to return those materials back to soil because we're losing a lot of topsoil every year and we're losing our soil nutrients. But it is a viable strategy to also incinerate some of that stuff for energy, provided, of course, it doesn't contain any additives or any other things that would cause some toxic emissions when you undergo that process. But certainly for a bio-based thing, especially the ones that are rapidly renewable, that's a very interesting alternative to composting.
Scott, do you want to go to some questions?
Yes, I would just add that we're recording tonight, so if you have a question, raise your hand and wait for me to come up so we can make sure that both the audience, there we go, both of the audience hears, the rest of the audience hears you, and we're recording it. So.
And remember, keep your questions tweetable.
Does that mean our responses have to be tweetable?
Well, thank you again for coming out. It looks like what we're talking about so far is paralleling a lot of my concerns as we evolve through this spectrum of transition to different materials. In reference to materials, my main concern is, again, we're resorting to a lot of secondary agricultural products. A product known as BioCradle, or is it BioCradle? It's like a styrofoam alternative. uses secondary agricultural waste products, basically, and a fungi, and basically forms styrofoam. So you're getting kind of a new kind of market, kind of new demand for these products. My concern as we increase in demand for these products are they going to dive into like the food production? You know, like that's the concern too, and also resources for like water and so forth, soil. Like we were talking about sugarcane. It's like the worst thing for like the Florida Everglades. You're basically draining out the bogs and digging ditches and draining it out, and you're losing that topsoil and so forth, and that just, you know, we're going to start a new production that's not going to be sustainable. Again, just sort of wondering your comments on that.
I think just to add one thing in that was a great question or series of questions, and I think
not at all tweetable.
But I think it highlights the fact that there's not a one-size-fits-all solution. There's not going to be a silver bullet or a plastic that's going to be, this is, or any material for that matter, that this is the material that we're going to shift to for everything going forward. And maybe sugarcane makes sense in certain regions of the world where it's currently being grown and harvested. I certainly wouldn't recommend, draining the Everglades to start to bring in a crop that probably shouldn't be there in the first place, just because we think we want to make all of our plastics from either corn or sugarcane or whatever. So we're going to need a whole suite of solutions. And in some cases, it might make sense to do sugarcane. In some cases, it might make sense to do oil-based plastics. In some cases, it might make sense to switch to steel and aluminum instead of plastic. But we're going to have to be really creative and attack it with a systems approach and think about unintended consequences of making these choices.
Can I just add to Jay's comment here, and that is you actually touched upon one of the fundamental principles of green chemistry, and that is, green chemistry is all about thinking about the future consequences and end-of-life considerations before you design a new molecule, design the process to make it, and put it into the environment. MTBE, the oxygenated gasoline additive that was developed many years ago, they did that for good reasons, but they didn't think about some of the consequences, and 10 years later we got leaking tanks, contaminating groundwater all over the United States, and adverse health effects. Well, if you apply these design principles right up front, you would be asking yourself these kinds of questions. You would be driving to answers that say, maybe this is not a good molecule. Let's look at some alternatives. And then the considerations go beyond just the economic in that particular case.
We'll get to this gentleman's question in just a second, but I'm going to use my prerogative as the organizer to ask you one quick question. You've been talking a lot about the process and the background of plastics, which I think is extraordinarily helpful, but the conversation hasn't gotten as much to building products and the products that are either changing or need to be changed, or perhaps are just fine the way they are within the building industry. So I'm curious if any or all of you can discuss the particular ramification of tonight's conversation as it contains to the built environment.
I forgot that we were in the National
Building Museum.
This one's teed up for Blaine.
Well, I just, as soon as you mentioned the shipping product, the packing product, one of my favorites is one by a company called Ecovative Design called Mycoply. Maybe some of you heard of this. It's a kind of insulation type foamed product that's made with agricultural waste and mushrooms. And they're supposed to be inert, but I love asking architects if they'd like to put fungus in their wall cavity. This is, in our values, not great yet, insulating values, but I think we live in a really exciting time. This is the thing that, there's certainly cautions everywhere, right? Red flags everywhere. Why we choose one thing over another, more than in my previous naive career as a young architect, where you just grabbed details out of shelves and did the thing like your boss did when he was your age, whatever, right? Things have changed so much. It's incredible that, and I don't know the numbers specifically. Recently, I heard something like 70% of building products have gone through some kind of eco-label study, or now have some green tag or something. Some of those haven't changed in terms of their chemistry, but others have. So it's an incredible transformation. To answer your question, I think many of you are aware of that, especially the architects or anyone who specifies products or reads a label. And there's increased demand for that. right? People always ask, well, I just want someone to tell me if it's green or not. You get this a lot, I'm sure.
Absolutely. That's why we created a program.
Just tell me. Just tell me. Give me a label, right? And we know that even that's not easy because as architects, whether it's plastic or another material, if it comes from a place where the chain of custody is sketchy and there's deforestation involved in some other country and lots of shipping, and it can be have the greenest chemistry in the world, but not be a green material when it arrives at the site. So it's a complex time. It's an exciting time too, though, and I think what it demands for all of us is to think. It actually demands a lot of kind of cross-disciplinary thinking and more integrated thinking, because we'll still use petroleum, right? And we'll still use the plastics. Hopefully we can mine the gyres, right?
Exactly.
Right? We should. But at the same time, we're heading into what folks have called the carbohydrate era from the hydrocarbon era, where we will look to renewable resources increasingly, including things like waste but competitively so. We have to really manage that. That's a tricky thing. I remember talking to Lester Brown, the environmentalist who's written Plan B and other books, when at the time, this is in fall of 2006, I believe, at the time when Iowa was starting to promise all kinds of ethanol, and it turned out to be more corn than they produce, or something crazy. It was this sort of mad rush to start promising foodstuffs for other types of industries. We've got medicine and obviously feed and building products, as well as energy and food. So we have all kinds of competing demands on these resources. So I think it's not enough just to say, okay, wait, the non-food stuff should take the non-food part of the plant, because as you mentioned, you could have industries that become really economically successful, taking wheat chaff or whatever, sorghum parts or whatever it is, and then competing with other industries that aren't as successful for some of the food stuff. So I think that's mainly it's more sort of a broad scale answer, is that we have to really think more holistically about the feedstock.
Thank you. For those of us who are sort of less experienced in this, I wonder if you could just give us a little bit of background on sort of the inputs, the materials inputs, and the relative greenness on the spectrum.
That's polyester. That particular one is PET, polyethylene terephthalate. And there's been some interesting work around trying to manufacture that same plastic from non-petroleum-based resources. PLA is also a polyester. It's not PET, but it is a polyester, and that's bio-based. And you can get a bottle just like that out of PLA as well. There's some other things in there in the label and whatnot that maybe are not germane to the conversation, but the base plastic is one that is probably one of the easiest to recycle, but yet it's only being done at about 20 to 25% post-consumer. So this kind of gets back to my point earlier about the systems thinking and particularly the end-of-life systems, the reverse logistics, the recovery systems, the recycling, the reprocessing. That's basically still in kind of the dark ages compared to everything else we're doing as a technological society. I mean, I got a smartphone that does 18 zillion things, but yet we can't figure out how to recycle a PET bottle efficiently and effectively. It seems kind of crazy to me.
So on the spectrum that you described before, where does that bottle?
That is on the greener end of the spectrum, because if we look at the two monomers, or the building blocks, the bricks, if you will, one is terephthalic acid, which doesn't have any real huge health concerns. The other one is ethylene glycol, which we do know does have some health concerns. But once they get reacted together, they're sort of inseparable at that point. So it's a new beast going forward.
Yeah. What I would say is that, and I agree with everything Jay just articulated, and I would just build on it and say that it depends on who you talk to, but we buy between 30 and 50 billion of those bottles every year just in the United States, and we only recycle 20 to 25. We do have the technology to recycle polyester. I think part of the challenge is we don't have the infrastructure, we don't have the incentive, we don't have the economics to collect the other 75 to 80% of the bottles that get sent to the landfill. This is stupid. We spend huge amounts of money to pump oil out of the ground. We convert it into this polymer we call PET, make the bottles, and then we bury it right back into the ground. Right? That's kind of foolish.
We to piggyback on that, we did some work early on with BP Chemical and their head of chemistry. I asked him flat out, what's going on with the bottles? What can we do? He said, I don't care as a chemist and a production guy whether I've got oil or old bottles. I will make new polyester out of either one. It doesn't matter to me. I can use either one. Now, what's easier for him to get right now, unfortunately, is the oil versus getting the old bottles.
Well, Hal, I know this was, I was going to say briefly on that question, though, we've steered away from Scott's question about keeping it building-centric. Plastic bottles, for me, are a great example of how narrowly we focus a conversation like this. It's not just because there are a couple of techno geeks on the stage, and I mean that as a compliment.
There we go. Thank you.
But it maybe 4 techno geeks on the stage. But it also, we spend so much time agonizing over making better bottles. How is it sourced? How is it made? How do we reclaim it, et cetera? Instead of stepping back and asking, why do we ship in our water from France to begin with? So to me, it's a great example of how, there's a horizontal spectrum around bottles. But if you get so focused on the specifics of that one dimension, you lose sight of the bigger question, which is, why are we carrying those things around to begin with? It's a recent phenomenon. Once upon a time, this water actually came out of the faucet in the wall over there.
Actually, it tastes pretty good.
Yeah, it tastes pretty good to me. I don't know. They probably poured it out of bottles. So.
Well, one of the things that Scott asked us to do.
Yeah.
One of the things Scott asked to do was to try to be factual, use information. So I was at a conference a couple of years ago, and I heard an architect actually deliver a talk, and he stated that China is forecast to build 40 billion square meters of new space in the next 25 years. 40 billion square meters. So for me, the first thing I did in my notebook was I circled that number in a big box, and I thought, I have no clue how much 40 billion square meters is, and I'll bet nobody in this room does. So I went back and I did a calculation. What's the largest building under one roof in the world today? The Pentagon, 6.5 million square feet. 40 billion square meters is the equivalent of commissioning 7.4 Pentagons every single day for the next 25 years. Just one country, China. And I will then ask the question, and to the architects and to the leverage that you get from buildings, think about the concrete, the steel, the window treatments, the plumbing, the electrical, the utilities, the furniture that goes into the building to operate. I mean, think of the impact that has. And then the flip side of that coin is there is no way that we can physically continue to grow and meet the demands of a growing population and a more developed population by the linear extension of the existing technologies we practice today. So we have to change the way we're doing things. And I think looking at holistically something like buildings gives us a great lever to do that, because it impacts so many materials that go back to fundamental supply and demand that the awareness and the education is key to solving this problem.
Well, absolutely. And as many metrics that we've heard point to about 40% in terms of building consumption of material resources, about 40%, and energy is another factor as well. But I think on that note, talking about energy, there's an incredible amount of embodied energy, even in the existing physical environment. And I think that precisely because of your point about the technical lack of feasibility, or at least at this point it seems infeasible, that amount of area could be achieved with entirely new material, that we have to really look and all that new embodied energy that will, it seems economically the case that we have to embark on a new era of really creative solutions that are adaptive reuse focused, because otherwise we're wasting. We're creating a lot of wastefulness, not only in terms of all the energy and new material resources, but also what exists in terms of the churn. I think we can't, based on that, and this is not just plastic, obviously, it's a lot of other materials, but based on that fact alone, we can't continue the old model of, and the sort of glorification of greenfield sites, which previously, there's so much development now, obviously, and development in cities proper, that there are fewer of those sites to begin with anyway. So you have to sort of raise and design afresh. But I think that, and what I teach students about too, is to really see those opportunities, those creative adaptive reuse opportunities, as ones that are actually phenomenally potent in terms of creative application.
On that point of building as a sort of gut instinct, I've always thought it's a little strange that we measure economic health by housing starts. So we're not doing well unless we're building. If we're not building, we're not doing well. Scott and I earlier talked about Ed Glazer at Harvard. He's an economist who just came out with a book about cities. But he, a couple of years ago, wrote an article where he estimated that if we didn't build another new house in the U.S. for 3 years, it would take that long. There's so much surplus of empty houses right now. It would take 3 years for the number of households to catch up with the number of houses. So we've got a lot of empty houses sitting around for a number of reasons. Yet we continue to think that if we're not building, we're not doing well. So it's a ridiculous idea that we have to keep making new things in order to be productive. So let's turn back to the audience.
Could you talk a little bit about the role of government here? I think that sort of a lot of the problems that you posed, in particular, just with the plastic bottle example, sort of 25 billion of them being recycled, but then the rest not being recycled. A lot of these issues seem to be addressed actually helpfully through regulation, which was sort of talked down to a little bit by the panel sort of at the beginning. So, if the EU has, made PVCs illegal, which I think somebody said, along with a bunch of other countries, why aren't we talking about sort of government solutions to sort of a lot of these problems instead of, sort of evolution and the market sort of letting things sort of happen, up until the entire planet is, sort of succumbs to global warming, et cetera.
Who wants to tackle that?
we have a saying in the office that regulation is a signal of design failure, and that you're obviously doing something wrong, and the government needs to step in and regulate that. So that's a design failure. But the recycling example is an interesting one, because I don't think that's necessarily a design failure per se. I think the right systems and the right value hasn't been placed on the material in that bottle. Recycling came about as a waste management strategy. So let's not kid ourselves. It's not about reusing materials. It's about a waste management strategy. And until that value equation gets flipped on its head and we start to see these things as actually valuable nutrients or materials, we're going to have a really hard time incentivizing recycling. We can mandate it. There's regulation. There's a bottle bill. There's lots of ways to do it. None of them work particularly well. Germany has the Green Dot program. They collect all their packaging. They have to. What do? They burn it. They incinerate it. So you're losing valuable materials, and until we start to look at it that way, I don't think any of these systems are going to necessarily work.
Well, what's interesting though. I think there's a role for regulations and legislation. My comments earlier about green chemistry avoiding the need for regulation was not to say regulations are bad, but they come about because problems were created, and you're trying to deal with and correct those problems.
Well, I was going to say on that point that I think that there's a sort of subtext to the conversation, which is an assumption that people make decisions, for instance, with regulation, the thought is that regulation prevents people from doing bad things that they would do otherwise without the regulation. But there's a sort of, we're not talking about whether people decide to do bad things or just unintentionally do bad things. And plastic is interesting. I showed that slide of The Graduate, and it's from 1967. So clearly, 40 years ago, 45 years ago, it was considered to be the way of the future. So 60s was really the great sort of breeding ground for plastics, strangely enough. As we've been talking, I've been thinking that plastic in some ways parallels the environmental movement in that. How many of you have read Silent Spring? Actually read Silent Spring? Because for those of you who aren't familiar with it, Rachel Carson wrote it in 1962, I think it was, and many consider it to be the launching of the modern environmental movement. The title refers to songbirds having not being around either because they're dead or they've migrated away because the environment is so inflicted with pesticides like DDT. And it's a brilliant book because she uses the kind of nuclear scare to get. She makes an analogy to nuclear scare around persistent toxins in the environment, and that's what really sort of got the attention that she was looking for. But the point she makes is DDT actually began. We think of it now as just all bad. DDT was never meant to be a super pesticide. It was used very sparingly by the Army Corps of Engineers and others to go into malaria-prone areas and spray it very sparingly on houses, and it's estimated to have saved something like 10 million lives by preventing the spread of malaria. So once upon a time, it was seen by looking through a certain lens as a miracle chemical. But the real lesson of Silent Spring really has nothing to do with chemistry or with pesticides. It's that we think something performs really well if we look at it with blinders on. And the lesson of that book is that chemists didn't talk to biologists who didn't talk to environmentalists or ecologists, etc. Plastic is the same. So plastic, to Mr. McGuire from The Graduate seemed like it was a super material because it's cheap and it does all these incredibly wonderful things, and it's only been over time that we've realized some of the challenges with it. And I think in the end the reason is because it's a brand new material, just like pesticides. Whereas, so you could see that the tenor of this conversation leading back to Scott's question about buildings. One of the questions I was going to ask all of you is that I know some architects who say that a building isn't truly quote-unquote sustainable unless you can build and operate it exclusively from materials and resources that are found on the site itself. So you can imagine a brick building where the bricks were extruded from the earth on the site. You can imagine a stone building the same way. You can imagine felling trees and making a log cabin all within your site. I can't imagine a plastic building that you made on site because it's a highly manufactured synthetic material. But I think this is a good segue to maybe bringing Blaine in to talk about emerging materials in the future of all this. Would it be possible to think about synthetic materials like plastics as something that you actually could nurture on a site and build the equivalent of a plastic log cabin?
Well, I think just to speak to the image that you raised of acreage from which you derive all the materials to create a structure of habitation is maybe a nice simplistic example or picture for the sake of simplicity. I can understand why some architects would conjure that image. At the same time, how realistic is that? How realistic is it that I think 3% of them, even in the economic downturn, I think 3% of America moves cities. I mean, people are mobile. People don't. 80% of America, something like that, it lives in urban areas where we don't have the acreage that would be necessary to grow the types of materials. I mean, even cities, as great as they are, here's an interesting thing, talking about ecological footprint. or let's say the land area that's required for harvesting, for the resources that would be required for a product, or in this case, let's say a city. Cities are touted as being really green, right? Because they share resources, that they're dense. I love cities. But at the same time, the researchers at the University of British Columbia that coined the term ecological footprint and really studied that phenomenon claimed that at the time, I think a city the size of Austin, Texas, a kind of medium-sized American city, a little over 500,000 people, would require the landmass of Vancouver Island, which is quite large, for its own sustenance. Forget industry, forget growth, just to live on that area. So I think we have to put that kind of image in context. I think in that image also applies to this notion of energy use, where people say, I'm going to go off grid, right? I'm going to get lots of PV panels and I'm going to get an acre of land, wherever, and I'm going to be completely self-sufficient. I think that also, some portion of the population can do that. That's fine. That's usually a good thing. But at the same time, I think the reality is much more interdependent, right? It's not completely dependent. It's not completely independent, but it's somewhere in between where we actually rely on each other, I think. Having said that, though, I think there's another dimension to your question. It's not just about the land from which, or the proximity, I guess, of the land where the materials are harvested. But certainly, I think in terms of the technology, and we've addressed bioplastics in the past, a few conversations here. In terms of the technology, we can harvest increasingly, or create plastics, let's say, increasingly from renewable materials, be they food-based or non-food-based. And there are a lot of different types of sugars, as you mentioned, Jay, from which we're getting bioplastic. And I think what's interesting, too, is it's not just thermoplastics, but also thermosets. There's some resins. Dr. Wool from the University of Delaware told me that right now industry is moving like gangbusters towards a future where we replace polyurethane as the synthetic version that we currently use with something bio-based and environmentally friendly doesn't have the toxins. And so I think that there's a lot of industry that's moving in that direction, and it will be more closely tied with a kind of agricultural tradition, but probably not in our backyards necessarily.
I would probably like to point out that in the United States we have an award called the Presidential Green Chemistry Challenge Award. It's given every year. This will be the 16th year that the award's given in June. And over the past 15 years, we've had 77 winners of that award. The vast majority are for commercially successful implemented operations for materials or processes. But the interesting thing is, for every award winner, there's between 4 and 5 applications that were submitted. So we have literally hundreds of examples of the successful implementation of green chemistry that are moving us down that pathway to greener. That sounds pretty good. But the fact of the matter is, we are in an ad hoc implementation stage. We're doing one-off applications, and what we need to do is put in place the incentives to drive systemic implementation of these principles of green chemistry going forward to solve these challenges. And just to let you know, I did remember the question that you asked. One of the examples that came to my mind is that, tire recycle, which is a pretty intensive material and energy product, was miserable until a law was passed requiring an excise tax to cover the recycling of tires. So every one of you, when you buy tires, depending on where you are, you're going to pay $1 to $6 for each tire that you buy, and that goes to fund recycling. Tire recycling rates are now above 80%. Okay, so you won't see in the future those big piles of tires, those fires, and the mosquitoes building up. But the point is, we had to put a law in place to fix the problem, because we didn't build the cost of sustainability into the original manufacture of that tire to account for its end-of-life issues. So, as we raise our awareness about these issues, I hate to say it, we're going to have to be willing to pay more if we want to solve the kinds of problems, develop the kind of products that are going to meet the needs of a sustainable society going forward. And I made the statement before that we can't achieve a sustainable society in the future by the linear extension of the existing technologies that we have. Most people nod their head because they agree with that intuitively. So the next logical question is, what are we going to do differently? We need to raise awareness, we need to apply the principles of green chemistry, and we need to accept that we're going to have to do things differently and pay a little bit more if we're going to solve these problems. And we need to not be myopic about it. It's been mentioned several times, but these are incredibly complex challenges that we're facing. They require diverse inputs in terms of conversations like we're having here with different technical, educational, geographic, cultural, experiential backgrounds contributing to those solutions going forward. And what works as a good solution where they got lots of sugar cane in Brazil may not be the right solution for Sydney, Australia, or for Beijing, China, or for San Francisco. So we need to go back to engineering solutions that fit the geographical needs and the availability of resources, and that speaks a little bit to your point about, being self-sustaining in terms of our habitat.
Yeah, I think sorry, there are a couple questions. How about the woman on the corner there? Because I know her, and she's going to kick me later if I don't point to her. So.
Hi. It seems to me that our effort to make plastics lighter and thinner is actually building in more and more waste. Because every time I go to the grocery store, I use those bags. One, they're very thin. They fall apart right away. You can't reuse them. So you're automatically throwing away these bags where in the past we might have recycled them for personal use, adaptive reuse. Same thing with the bottles. They're so thin they fall apart. Why not go the other direction, make it more substantial so that it can be reused? And in the same way that we do this bike share with our bicycles around the city, that you come up where all the bottle companies basically share the same bottle form, and that you don't have to ship all this waste to get recycled. I used to go and exchange glass bottles and get 5 cents for them. I go crazy to think that we're breaking it down to remanufacture. Why not reuse the product for a similar use?
Yeah, I think it's a great question. You could apply it to buildings as well. I mean, most of the housing stock built today is the equivalent of the plastic grocery bag. It's meant to be disposable. It's meant to be. It's not meant to die quickly. That's just a consequence of it meaning to be cheap. So, in order to make things that are affordable, we make things that fall apart really readily. So I think this goes to Bob's point earlier that we need to be prepared that certain solutions are going to have different economic models. So instead of thinking, okay, well, if you built a more substantial house, that you would think, well, that's not going to work in this market, to pay twice as much for a building that might last 3 or 4 times as long. But if you look at the life of it and the total economics of it, it's actually going to save money over time. But we tend to look very narrowly at first costs.
Right. Absolutely. I'd just like to put a plug in here for the role of designers. I think it's really imperative that designers, as makes sense, and in response to your point, think of multiple lives of products and buildings. I think for example, what Sam Mockby's Rural Studio has done is brilliant, where students are acting like chefs in the kind of farm-to-food movement, if you will, within the culinary world, but with architecture, and saying not in a catalog, what do we pick out of a catalog to make our building with, but rather going out into the field. Oh my gosh, we've got 20 windshields. I'll pay $200, right, at the waste dump, and I'll make these into this beautiful new curtain wall. I think we have to think more like that. Maybe it's not quite in that vein all the time, but I think if we can even design, I don't know if it's windshields or a bottle or what it might be, but design products and buildings with thoughts about those future lives, that would be a whole new design challenge, but I think a worthy one.
I appreciate, but I have no argument with your social science conversation. I think most people here are in agreement about policies, but we've got some pretty sharp chemists up here. I've noticed, if we could take apart that for a moment and go back to physical sciences, the countries that seem to be most acknowledging and advanced tend to be those that are very highly dense, like Holland, Japan, Israel, that are also somewhat resource deprived. Australia. What are they doing, physical sciences, that are different than, not social, but physical? I mean, they are ahead of us, would you agree, in what they're doing?
I think the answer is a little bit more nuanced here, but I would give you the following example of where some trends are going. If you ask me today how many green chemistry centers there are in the United States, there are federally funded centers of excellence. There are 0. There are good academic institutions which are centers of excellence that do get some government money. But if you compare that to what's going on over in China right now, China is a mess from an environmental point of view, but China gets the fact that green chemistry is the key to achieving this sustainable future. There are more than 20 green chemistry centers that are federally funded by China right now. And you start looking at the number of Ph.D.s that are being granted, you start looking at the number of patents that are being issued, you start looking about the innovative design of new products and materials that are coming out of there. They're about to eclipse the United States. This has been our power alley for the last, 60, 70, 80 years, certainly since World War II, and we're about to lose that leadership potential. And I think that the bottom line is they understand that they've created a crisis in their country with respect to the environment, and they're going to invent their way out of that crisis by applying these new principles going forward. And here's the sad part about it. We're paying for it. Because where are they getting the money to fund 20 green chemistry centers? It's our appetite for all of these rapidly disposable materials that are just convenient. The example of the shopping bags that fall apart. I mean, my wife, my daughter is carrying those cloth bags back and forth to the stores every time they go now, and they get upset if they forget their bag. That's just a small example of the little things that we can do as individuals that may not seem like a lot, but when you integrate them over 330 million people in this country, can start to have an impact. If we all switch to compact fluorescent light bulbs, or wait until the LED light bulbs come out and we make the commitment to switch, do they cost 20 or 30 bucks a piece? Yes. Are they going to last for 20 years? Yes. Are they going to cut your energy consumption by 60, 70, 80%? Yes. If we all did that, it would have a big impact.
So what I got out of that story is you don't do the grocery shopping in your family.
He does, but he doesn't have his own bag.
Very good.
They don't give him his own bag. He has to resort to the plastic.
Well, they hand me when they send me down, okay? They hand me the cloth bag, so there you go.
Okay.
Lance, we actually have a tweeted question.
Oh, good.
Are you serious?
I am serious, yeah.
That's actually possible?
That is possible.
Count the number of characters.
From Architect Magazine. Are mushrooms the new plastic when it comes to building materials? You had mentioned earlier, Blaine, about mushrooms.
That is a very tweetable question.
Not a very tweetable question.
Are mushrooms the new plastic?
Psychedelic. Discuss.
Are mushrooms the new plastic? Well, certainly there are biocomposites made with mushrooms.
I don't know that I would call those plastics, though. They're not necessarily polymeric in nature like a plastic by definition.
Right. But are they making building materials out of mushrooms? And
they
can you talk a little bit about that? What can you make out of a mushroom for building materials?
Well, suppose you ask the question: what can nature's chemical factories make for us that can make our life more sustainable? So we've learned how to control. We learned how to control the genetics of organisms, and there are companies right now that have engineered plant cells to produce plastics. Now, let's not get into debate whether plastic's good or bad, but if you talk about the creative process of coming up with new ways to tackle problems, plants grow by harvesting the energy that's free to us from the sun. So that's the energy that goes into building the plastics. Then they harvest the plastics from the plant cells, and they can use those to make materials. So it's another sort of creative step in this evolution of how can we derive materials that are more sustainable, more creative, and do it with a less intensive manufacturing process. I mean, there's enough energy to hit the planet of this Earth, of the surface of this planet, every single hour to meet the entire energy demand of this planet for one full year. So we need to get smarter about mimicking nature the way she captures solar income and converts it into usable energy. Well, the thermodynamic efficiency in the United States has been estimated by the U.S. Department of Energy at 2%. 2%. That means 98% of all the coal, the oil, the natural gas that we use to produce energy is wasted through the inefficiencies of the transmission process and that sort of thing. So that tells you something about, you know, how sophisticated our technology is going forward.
Scott, I think your response should be, is plastic the new mushroom? Rather than anyway, sorry, there was
is that plastic mushrooms?
Hi, this question's for the entire panel. How would you look at or comment on the trend for people asking for plastics? I mean, like now it's the consumers who are asking for plastics more than the suppliers actually pushing it out. So, how would you comment on consumer demand being the new I guess a new push for plastics?
Are people asking for plastic? Yeah. Are they? In what context?
Are you speaking about consumer goods like cheap toys or tools or?
The demand is coming from developing countries and what you call the third world countries, and they're asking for plastic goods because for them it's an aspirational. It's aspirational. So the question is, how do you, I guess, try to? I mean, how would you look at that? That's my question.
Right, it's not a bad thing. I mean, I have a hard time putting value judgments on plastics in general. I mean, I think I've made my point kind of clear that there's a really important place in our society and their society for plastics. But if you're going to make the demand for them, then what are you willing to do at the end of use phase to make sure that your plastic isn't in the Pacific Gyre or in the bottom of a landfill or in the bottom of an incinerator?
Yeah, I think what's interesting is to visit some developing countries and to see what they do or don't do with their plastics. To visit a country like Cambodia and see ditches filled with PET or other bottles, because there isn't. I mean, talk about a lack of an infrastructure to collect and deal with that. And so, but at the same time, like some other technologies that have been adopted in developing nations, there might be a chance now to use, let's say, PLA or other types of plastics that do biodegrade, so that they actually sort of avoid some of the pitfalls that we've had with that waste problem.
We can perfect our system.
Right.
We have time for one or two more questions and then some final thoughts.
I was wondering, putting aesthetics aside and your opinion of how it looks aside, things like that, vinyl siding, I'd love to hear your opinion on it, because when the Healthy Building Network calls it one of the biggest, potential health disasters in the country. When you talk to the vinyl siding industry, they say the chemicals are inert, there's so few, they don't have phthalates, and their life cycle assessment is second only to wood, and is the only siding product that can be recycled back into itself. I'd love to hear what you guys think of vinyl siding.
How much time do we have, Scott?
I'm curious to hear what the architects have to say about this one.
Well, you asked this aside from the aesthetic aspect of it, right? Well, I think some of what you just said there exposes the limitations of life cycle assessment, because there's only a piece of the puzzle, and I think the kinds of things that Bob has been stressing tonight, the principles of green chemistry, really, there isn't a very, maybe Jay would say it's cradle to cradle, but there aren't a lot of elegant solutions for looking at the kinds of things that LCA considers and the kinds of things that green chemistry considers, and they're sort of looked at separately. So many products that are touted as green look exclusively at LCA type considerations. So what's the, how many resources are we consuming over a certain period of time, and not look at the chemistry of it. I think in the end, if you ask yourself, well, if I've got wood siding versus vinyl siding, which would I rather have in a fire? Which would I rather my kids, inhaling if my house burnt down? Then you start to see, what the issues are?
I think it's a tricky type of application because I rented a house once where that was sided in vinyl, and one whole side of the part of the back was kind of melted inward in this big concave shape because that's where the grill had been with the previous owners. And also talked to window manufacturers that say they can't produce frames and colors that are dark because they melt.
They get too hot.
So you start to wonder about this. But at the same time, we have a lot of PVC, right? There's a huge volume of PVC that, so the Outdoor Advertising Association of America, for example, a couple of years ago, was going through this big transition where vinyl facings are no longer used by their members for billboards. But then we have all this vinyl billboard facing material that's then turned into things like bags and construction tarps for construction that can be reused many times. They're thicker than the new stuff that you buy at Home Depot, for example. So there's a market, and there are uses that are probably safer, I would say, for vinyl. We should look for those uses, but at the same time, I'm not a big fan of the siding myself.
I'll just say briefly, I think for me the question inevitably comes back to aesthetics and not just independently of the kinds of issues that we're talking about. I think there's one of the reasons why there's such a big market for vinyl siding is because it can look exactly the same 5-10 years down the road. So it's part of this of a culture of newness. Steve Jobs says that on the one hand, Apple touts their products as being some of the greenest in the industry in certain aspects, right? On the other hand, he says if you want the latest and greatest of any of their products, you have to buy them every year. So there's an inherent waste that goes to that. And one of the things that makes Apple's products so sexy is that, the first time they start to get a nick, then they start to feel old. It's the same with vinyl siding. It's invented in order to make a house look new forever. Instead of thinking, well, maybe the weathering that comes with natural materials is actually a really good thing, instead of thinking of, wow, my house is falling apart, maybe collaborative siding, go to Nantucket and look at the way that it's weathered. It's the whole aesthetic of that culture is based on that, and it's something the rest of the country is trying to deny, right? So for me, the aesthetics are part of this because I think the reason it's a popular product is because we're trying to pretend that time doesn't exist.
I have a related thought, if it's a good time. This is kind of a closing thought, but something for all of you to think about is, and product manufacturers and architects and engineers and a lot of us are focused on this interesting issue about durability in the physical environment and the desire for that, right? Like a product like vinyl siding, which does so well, versus persistence and the lack of or the kind of fear factor that develops when you show the gyres in the oceans that we don't want. And there's this kind of strange conflict that emerges, right? And bioplastics manufacturers have told me, well, when I've asked about biodegradation, which we want, right? We want the water bottle to biodegrade. We don't like this idea that it's still there, it persists. But at the same time, what about buildings? What if we're making buildings out of bioplastic components in the future? We don't want those to biodegrade, right?
Until we're done with them.
Right. And they said, well, wood framing biodegrades. It's just very slow. And so there are time scales. And I think something for anyone involved in designing, specifying, constructing the physical environment with some of these new materials, some of these new bioplastic replacements of existing plastics to think about is the notion of time scales in design, and the notion that there is that time dimension to design, and that you include that in your programming. Right? It's not just a space program or a material program. It's also a time scale program, so that you can think about, well, is this a 100-year building or 25-year building? We do a little bit of that now, but there's so much emphasis on kind of upfront first use that I think some of we almost program time into materials, and how we reuse them will really help.
So maybe with that, some closing thoughts and any ideas that you'd like to have the audience walk away with tonight? In no particular order.
Well, I guess I would say, first of all, thank you for taking the time and energy to come in and be part of the discussion tonight. And my encouragement would be that each one of us individually can make a difference. When you walk into the store to buy something, ask for materials that are sustainable. Educate yourselves on what are the criteria by which that judgment is made. Ask for more of it. My example might be what's going on in the cleaning products industry. There's a revolution there that, we've really done a good job of making a lot of progress, taking some bad things out of the cleaning products that go into your homes, both for your personal use and for use in your dwellings or for your cars. And that is a direct response from consumer demand. The other thing I would ask you to consider is, a lot of what happens in our society is influenced by who we put in this particular city. And, I'm involved in a lot of dinner and lunch conversations with people, and everybody's talking about all the problems and the frustrations, and we're not making any progress, and the Republicans are fighting with the Democrats. And I finally say, you know what? We all agree on that. What are we going to do about it? Mm-hmm. And one of the things I've suggested we do is let's start finding some scientists, some engineers, some doctors, some architects, some technically trained people that understand the challenges that we're facing long term for the future, who would make a commitment for a cycle of public service, not a 50 or 60 year career to feed at the public trough of funding, but to go there with the commitment to do the right things and stop fighting amongst one another. So this is not a political forum, and I'm not a political guy.
But you've just been elected.
Yeah.
For that particular 5-year window.
Manager over here. Thank you.
I would echo what Bob said in the first part of his little monologue, and that don't underestimate the power you have as individuals and as consumers. And I end a lot of my talks with that statement to say, look, you guys are ultimately voting with your dollars, and the things that you buy and the products that you support. That sends a strong message to the manufacturers, a lot of whom are our clients. So I know this works. So don't underestimate that. You do have a lot of power that you don't realize. So demand better products, demand better stuff, healthier, safer stuff.
Well, I would just like to emphasize again the importance of design in all of this, because talking with, and other architects have said this too, but most recently I was speaking with the architect Takaharu Tezuka in Japan, and he said, earthquakes and other natural disasters don't kill or destroy most buildings. It's because they're not beloved, right? Because they're not the value that's inherently encapsulated within a structure in the developing world. The client eyes, let's say, if seen as mediocre or not beloved or not special, will lead to that particular structure's demise much more quickly, probably proportionately, than any other kind of demise, like technical obsolescence, let's say. So, and that's not always the case, but I think we know that design is important. Even if we stop drinking water out of plastic bottles and we carry around our nice thermos, we know that in terms of product design, if that's kind of generic, not really memorable thing, then we'll probably let that sit in the shelf and eventually throw that away too. So I think design is really important as a way to galvanize and excite and entice and draw in people. And I think the more that we can make a case for that value, no matter if it's a product or a building or infrastructure, then that can endure and can again speak to these future generations of use and inject some intelligence, if you will, into that substance.
I was just going to thank you, Scott, for putting this together, but also thank all of you for sticking around, because much of this is pretty technical, and I'm amazed there's so many people still in the room. So thanks for coming.
We didn't put him to sleep anyway.
And thank you to all of our great panel for putting on such a great program.